Okay, so let us start. Okay, so today we are going to continue with chapter 7. Chapter 7 is about modeling. And the last class, we discussed the first model is about linear regression. So linear regression is about a prediction of continuous value. Okay, continuous value. And we discussed a couple of different approaches to do linear regression. We discussed a statistics model. We also discussed machine learning model. And in machine learning, we also introduced, so besides the linear regression, linear model in scikit-learn, we also introduced the neural network one. Okay. So that's last class's model. So today we are going to learn some new models. The first is about logistic regression. Okay, so even though here the name has a regression, but this is not a regression. So logistic regression, basically it's a classification problem. And it's different from linear regression. Linear, it's about continuous value prediction. Okay, classification is kind of like if you recall, like image recognition. Okay, like have photo. Okay, so computer can recognize if it's a cat or dog or a plant or some animal or car, something like that. Okay, so that's called a classification problem. Okay, so logistic regression is one of the approach to do classification. And for logistic regression, the classification it's not just a predict, it's this object or it is not, or it is this category of object or not. It's to predict. So here is the highlight is the probability. Okay, that the dependent variable y. So in statistics, we call it dependent variable. And if you recall, in machine learning, we call it target. Or you can call it output. Okay. And so for logistic regression, it's about the probability that the dependent variable or target or output belongs to some binary output. So this is for uh, the binary classification. If it is a multiple class classification, then it's not just so it's you have more than two class to classify. Okay. So it belongs to the binary outcome based on one or more independent variable X. And in machine learning, independent variable X, we also call it features. Okay, so that's the idea. So it's about the probability belongs to a class. Okay, it's not is this class or not this class. It's about the probability. And the logistic regression, the key mass behind the logistic regression is the logistic function, or we call it a sigmoid function, okay? And sigmoid function, so the plotting, if you plot it, it will look something like this. So basically, it's kind of you squashed some uh, we can also think like later I'm going to explain like some linear representation and it kind of squashed it, okay, so that it can tolerate like a more wide range of your sample distribution, and also it constrain the output belong to 0 and 1 because it's about probability, okay, and because it's a probability, so here we set up the threshold. So threshold is 0.5. So if the probability is above 0.5, then you will just think, okay, the output is going to be 1. Okay, because the output for the classifications either 0 or 1. Okay, so with the probability, if it's above 0.5, we call it a threshold, then we say, okay, it is 1. If it's below, then we say, okay, the class is going to be 0. So basically, it is this class. So it's yes or no for the class. Okay. And so this is the sigmoid curve. Sigmoid function or logistic function. Okay, the sigmoid function, logistic function, the math formula is given like this. So regarding Z, okay, and in the real world scenario, the independent variable may not just have a single one. Is it not just a single value? May be multivariate, okay, not a univariate. So if that's the case, then the Z is going to, so what all of the independent variable is x1, x2 to like xm, okay? And we are going to, so our goal to do the classification is you're trying to find all of those coefficients. So these coefficients, those coefficients in machine learning, we call them weights. And if you recall last class in linear regression, we discussed the alpha and the beta, if you recall. So the slope and intercept. So this W, the weights, yeah, similar. It's coefficient. Yeah. So it's a linear combination of the weights and the independent variable, or the weights and the features. It's a linear combination, okay. And this linear combination, then we assign it to Z, this variable, okay. So basically this Z in machine learning, we call it net input. Net input. Okay. And then the net, so the logistic regression is to reflect the net input relationship, okay, regarding the prediction Y probability. So that's the overall idea about logistic regression. Okay, so that's the concept about logistic regression. Okay. Okay, let's understand it better. Okay, so I have some more explanation. So here it gives us a diagram, okay, to understand the previous explanation. So here we have the x1 to xm. So those are independent variable, or we call it features. And over here, this is 1. Okay, so this is for the constant term. Okay, and for each of the independent variable, including the constant term, we assign some weights. So basically, then in this case, the W0, then it's a bias term, okay, in machine learning. And you have the linear combination of it. So we have the net input. Okay. And net input, then you apply sigmoid. We call it, in machine learning, we call this sigmoid activation function. Activation function. Okay. And so you have the probability to predict the dependent variable y belongs to 0 or 1. Okay. And with that, based on the threshold, then you can predict the class label. Okay, so that's why we call this a classification problem. Okay, so previously I also explained, okay, so based on the sigmoid function's output, if its threshold greater than 0.5, then you predict it's 1. Otherwise, you predict it as 0. So if it is that class or if it is not that class, okay. Okay, so over here I want to introduce another concept about gradient descent. Okay, so this concept is a fundamental concept for machine learning. And over here, I use the case of add line. Okay, add line is also for classification, but instead of using logistic regression, so add line, the activation function basically is the linear combination of the weights and the features. Okay. So it's more like a linear regression, okay, but it's not, because this is for classification. Okay. So based on this, it's so this is serves like a separation between two classes. So this is a class. If the point fall below, then it's another class. Okay. But the drawback with add line is if you have some points like off the area, okay, then it may cause the line, like changed a lot in the direction. And if it changed a lot in the direction, then the sample point is supposed to be in one class, then it may fall to another class. Okay, that's why if we use sigmoid, so the idea is if you use sigmoid, you see, then it's uh, so it's avoid the sharp change of the linear lines, direction change and change the classification of the samples. So the tolerance level is higher. Okay. But here we use Adeline. The concept here is I want to introduce like the cost function. Okay, so for Adeline, the cost function, there are some similarities between this cost function. And if you recall in linear regression, we learned OLS. Okay, so that ordinary least square concept to find the optimal alpha and the beta, okay, the intercept and the slope. So here, a similar concept, the cost function, it defines it's just sum of the square of arrow, okay. So so this is the actual dependent variable, and this is a predicted dependent variable's value. Okay, so in Adeline, it uses this and it defines this sum of square arrow as a cost function. And similar concept for the Adeline is to try to minimize the cost function, okay? And with the minimization of the cost function, and over here, this phi basically is the sigma Wixi, okay? So that's why this function is regarding the weights W, okay? And if you try to minimize, basically you need to take a derivative about each weight. Okay, so take the partial derivative. Okay, so that's the idea. And this derivative, the cost function's derivative to weights, this is called gradient. And then why it's gradient descent? Okay, so what is that idea? So we try to minimize the cost. So this J is cost, and because you have multiple features, so each feature has their own weights. Is it so? J is regarding the function of weights because weights is unknown is what we are trying to solve. Okay. So this is gradient. So in machine learning, we are not going to directly use math to try to solve the math equation to find the solution for weights. Okay. What we do is so this curve represents the cost function relationship with just a single weights. Okay, so in that case, then it's a quadratic curve. Okay, with this quadratic curve, then the slope of any point of this quadratic curve, basically it's a gradient. Okay, so the gradient descent, the concept is once you know the slope, then it's the cost functions derivative to the weights. Okay, and then you go to the negative direction in this case, okay, in this part. Then you see, so the idea is, so this is delta W. So you can define certain unit, and we also call it a learning rate, okay? And with the learning rate, times the slope, then you can basically find the increase or the decrease of the weights. Okay. And once you know, and over here, you can set some initialized weights. Some initialized weights. Okay, you can assume. Anyway, it will be on this curve. So then with the weights decreasing for each step, then you will getting close and close to the area that the weight will lead the cost be the lowest, be the minimum. And the goal is to minimize the cost. So when the cost is minimized, then the weight, so this weight, then it's going to be the optimal. So that's the whole idea about gradient descent. Okay, so it involves number of iterations to getting approach, or from this direction to increase the weights. Okay, the delta W. Okay, then over here to get, because we know the weights increase or decrease for each step. So each step you can update the weights, and you're going to then finally approach to the optimal range of the weights. It's very hard to get exact, but in that range, okay. And so the key is to find the change of the weight, and the change of the weight, then we can represent it as a learning rate times the derivation or partial derivation of cost function regarding weights. Okay, and so the cost function, for the cost function, you can select different. So based on the different scenario, the cost function is going to be different. Okay, so this case, then it's specifically for the add line. Okay, add line, then because its activation function is a linear combination of the weights and the features. So you will have this result. So here, be also careful. Okay, different cost function. So cost function is different. Okay, based on the model. Okay, so based on model. So model's difference then will lead the cost function also be different. Because different model, the activation function is different. Like, add line, then it's linear combination, okay? But for logistic regression, then the activation function is sigmoid. And because of different, then the cost function will also be different. So we already explained, okay, so you take derivative. So if it is add line, then we will have this result, okay? And then let's come back to logistic regression. Okay, so then for logistic regression, the cost function is different because the activation function is sigmoid function. Okay, and the sigmoid function is regarding probability. So over here, we try to not minimize, we try to maximize the likelihood. Okay, because you try to maximize the likelihood to predict the point or the sample point, we call it the data point, to be some class. Okay, the higher the better, is it? So over here, so this is a probability, and then based on sigmoid function, it can be written like in this case, okay. And then we try to we can take a log, okay, and we try to maximize the nature log of this equation. And then for logistic regression, then the cost function is defined like this, okay. So this is the cost function for logistic regression. And because in logistic regression, it's classification. So classification, then the dependent variable y or the target, it's either 0 or 1. Okay, because if it's either 0 or 1, so basically your cost function can also be rewritten in these two cases based on if y is 0 or 1. Okay. And our goal is still to minimize cost and predict correctly. Okay. Okay, so that's basic, very very general and rough concept about logistic regression. Okay, so for logistic regression, in this chapter, we introduced two approaches to do it. And the first one is use that statistical model. Okay, so use the use this statistical model, okay, from this package. And it's also pretty straightforward, okay. So you just invoke this logic function, okay, and then you plug in the dependent variables points and the independent variable, okay, and then you try to fit off the values, then it will give you the output. Okay, so we will see in our example. So you can see the model, to use the model is pretty straightforward, okay. And we can also use the machine learning, the scikit-learn library, okay. And it's also pretty straightforward, but you need to import logistic regression. It's still belong to the linear model sub-package, okay. So you create a logistic model, and then you fit, and then you can predict. And we will explain and how to measure the performance. And in machine learning, there are a couple of different metrics that you can use for the performance measuring. And I also want to introduce very briefly about the concept of neural network, because in our example, we also use a neural network model to also do classification, prediction. A neural network can also do some other tasks, okay, not just classification. It can also do regression, okay, and generative AI and compression, okay, so some other tasks. So the basic idea about a neural network is the idea is it involves the neurons, okay, and over here we consider multi-layer. Okay, so a neuron, we call it a perceptron. Okay, and in so for over here, what we consider not just a single layer, okay, it's a multi-layer perceptron. So multi-layer perceptron basically is a neural network, okay. And also in this case, it's a fully connected neural network. So what a fully connected neural network, the idea is, so in this case, we have this input, so the X. So that's the independent variables, okay, in statistic. So in machine learning, we call them input, okay. So for each feature, so each one of that is a feature. So for each of the feature, and you also have a bias term, okay? So we represent, you can represent, basically here, A0 to AM, it's X to XM, okay? And this corresponding to the constant term. So for each of it, and we call this layer input layer. So this is the first layer, okay? And then the second layer, we call it a hidden layer. So you can set a certain nodes, or over here we call it neurons. Okay, you can set a certain neuron. So here you have the input neurons, and here you have hidden neurons. So you can set like 10 or even 100, okay, the neurons. And for each of the neuron, and then if we take a look, you will see for each input neuron, it's fully connected to all of the neurons on the second layer, hidden layer. Okay, so that's over here. And for the connection, then you assign a weight on it. Okay, for each, then you assign a weight. So here's W01, and for this case, then it's W02. So 0 connected to 2. Okay, for this one, it's W0, then H. So it's connected to H neuron in hidden layer. So for each of this line, basically it represents a weight. Okay, and the same thing for the next neuron. Okay, so that's about the hidden layer. And then over here, it also shows the output. Okay, so basically, these outputs in our logistic regression case, then it's the probability. Okay. So here you have this output and then outputs, and then with the threshold, you have the classification defined. Okay, so that's the targets or the dependent variables. Okay, so over here for each of the outputs, okay, it's also represented as neurons. Then the hidden neurons also fully connected with the output layers neurons. So this whole idea is from input and to the output, okay? And in the middle, you can add certain number of hidden layer, okay? And the connection between them are all weights. And all of the weights are unknown. And the goal for the training of the neural network is to find the optimal ways to connect all of them together so that when you have this input and through this neural network, then if the weight is optimal, and then the output will be very close to the real outputs. Okay, so that when you have new sample or new data, then the predicted result will be correct. Okay. So this is the idea about a neural network. So in our example, we will also see we can also use this neural network to do classification. Okay, so next let's go to the coding part. Okay. For the coding, this is, oh, that's master class. Okay, so today we will start with logistic regression. Okay, for the logistic regression over here, we will use this data set. Okay, data bank authentication. It's also a CSV file. Okay, so let's take a look at what the file looks like. So using pandas, we can read the file, okay, get some header. So take a look at the first five rows. And we can see the first four row, okay, or the first four column are some decimal point. And the last column are like 0 or 1. Okay, if you take a look at the complete data set. So basically, for the last column, it's Y, okay? And the first four column are X, okay? And a total number of samples, we have 1372. So then let's see, how do we do it? Okay. So we first needed to get the X and Y value, okay? So if you recall from pandas, you can specify the using slicing, okay, to get the four independent variables, okay? And this is indexing to get the Y values. So once we have the value, because they are already numbers, so we don't need to do any conversion, okay? So first we are going to use statistical models, okay? And use its logistic regression. And you can plug in the X value and the Y value, okay? Pretty straightforward. Then you just call fit. And then here for the summary, it will give you the result. And we can take a quick look of the result to get some idea about this logistic regressions classification, okay? And here it shows, okay, total number of observation and degree of freedom, because here we have four independent variables, so that's why the degree of freedom of the model is 4, okay? And then you minus and also consider constant term, so that's why here is the degree of freedom for the residual, okay? And the method it's used here, it's use maximum likelihood estimation. Okay, so this is maximum likelihood estimation, because it's logistic regression, is it? And logistic regression is about the probability. And if you recall in machine learning, we also consider the likelihood, okay? The cost function is also about the likelihood. And with this method, okay, the R value, if you recall, or the adjusted R value, is it? And it's between 0 to 1. And if it's close to 1, then that means your model is a good model, is it? So here we can see the R value is also pretty high. Okay, so that means the model is pretty good. And AIC and BIC, if you recall last class, is regarding the model's complexity, okay, and try to not let it too complex, because it's too complex and then it can cause overfitting. Okay, so that's about AIC and the BIC. And also here we have the log likelihood regarding the null hypothesis, okay, and the p-value. And also over here, the result also gives the constant term and the four independent variable, their coefficient, okay. So basically, this coefficient is the weight, Wi, okay. We can, and here is a standard error, okay. And here is a z statistic, and here is a p-value. And from p-value, we can also see it's pretty lower value. Okay, so that means the result is also good. And here also give you the 95% confidence level. Okay. So this is output for the statistical model. So next, let's take a look at the machine learning model. Oh, before we move to machine learning model, and over here, we also do some plotting, okay, regarding what the model's prediction. So the model can predict and with the probability, okay. And then we do the net input, okay, by net input. And here, this is the sigmoid function, okay. And then we try to plot the predicted value and versus the actual value, okay. So the result looks like this. So we can see it's pretty close. Okay, so that's why the result is pretty good in this case. Okay, what next we are going to do is using machine learning's logistic regression. Okay, and for machine learning, it's a little bit different from the statistic. As generally speaking, here total data points, we have 1372 data points. And in the statistics model, you apply all of them to that statistics model. Okay. For machine learning, we are going to split this total number of data points into two parts. We have training data set and the testing data set. That's normally what we do, okay, in machine learning. So that's why over here, we import this train test split. And in this case, this is the first step. You need to call train test split. And this is the ratio. So the ratio, normally you apply larger ratio to training. So in this case, you apply 80% of the original data point to training and 20% to the testing, okay? After that, you create a logistic regression model, okay? With this model, so this is a logistic regression model already created. When you train, so here we train the model, you use the training data. So be careful, okay, use training data set to train the model, okay. After that, when you do prediction, we use testing data set to test the model's accuracy and some other performance metrics. Okay, so be careful. When we do predict, we use testing data set. Okay, And after that, then you can evaluate if the model is good or not. Okay. For model evaluation, we have different metrics to measure. And over here, we first just use machine learning's accuracy score to directly measure. So what to measure is for testing data and its predicted value. Okay, so this is actual, and this is at y hat. It's predicted. Okay, and as you can see, the accuracy is pretty high in this case. And there are some other performance metrics that you can do the model evaluation. Okay. Model evaluation and using performance metrics. Okay, and over here, so you can use scikit-learn directly give you the metrics. You can use confusion matrix and classification report give you more idea, okay, about the model's evaluation. And later I'm going to explain about this two concepts, okay? So confusion matrix, you just plug in the testing, the actual and the predicted. What it looks like this. Okay, because this is binary classification. So you just binary classification is either 0 or 1, okay? And so that's why the confusion matrix is 2 by 2, okay? So on the diagonal, so the diagonal is correctly predicted. And non-diagonal, so those are the wrongly predicted. And you can see it's not that high, the number, is it? It's just 2 of the predicted. So this is a confusion matrix. And then the classification report. So for classification report, you will see it's more including more information. Okay, so it includes precision, recall, and F1 score. We will explain. Okay, and here is a number, and over here it's represent which class. Okay, about the performance measures metrics, and it also gave you the accuracy and the weighted accuracy. Okay. So besides accuracy, you can also consider confusion matrix, precision, recall, F1 score, okay, for your model. And what next part try to show is to try to show how to use neural network for classification. Okay, we still use the same data. Okay, same procedure. You need to first split the original training, the original data points, data set into training data set and testing data set. So it will automatically split for us. Okay, and after that, we are going to use a neural network, okay? A neural network model from scikit-learn. And for complicated and large neural network, normally prefer to use like a TensorFlow or the PyTorch, okay, package instead of scikit-learn. Okay, but scikit-learn gave us some idea about neural network. And for this case, we use multi-layer perceptron. Okay, so you import the multi-layer perceptron for classify. And if you recall last class, it's a different one. Okay, so for regression or regressor, okay, different. So with that, and we define this neural network model. So hidden layer size, it's just take with the default one, okay? The maximum number of iterations, so that iteration basically is regarding the weights, how many iterations it will go. So it's to prevent, it depends, sometimes it may not reach this point if it converges fast. So if gradient descent converges faster, then it may not run to this point. But if not converge, sometimes it may not converge, is it? Then you don't want your iteration going forever, so you need to let the iteration stop. Okay, so that's how we set this. So after that, similar concept as logistic, you do the training the model. After training model, you can do the prediction. And with the prediction, and this time the measuring performance, you can also use R2 score and mean square error. Okay, so the R2 score, and previously we also learned the R value. The R value is between 0 to 1. And if it's close to 1, that means better. And for the mean square error, we want it to lower. The lower, the better. Okay, so we can see, because after you have the result, you can collect the performance metrics. And we can see the performance metrics. In this case, R square is 0.95. Pretty good, is it? And the mean square is very low. Okay, it's 0.01. It's quite low. So that means the result is pretty good. And the accuracy is 98.9%, also pretty high. Okay, but we can also see neural network in this case, the accuracy not as good as a logistic regression, but the accuracy doesn't 100% reflect the future prediction. Okay, because it may be that logistic regression may be overfit. Okay, so we cannot see just based on this value that means that model is better than this, okay? Because maybe the neural network, it also considered regularization, okay, to prevent overfitting. And you can also collect the confusion matrix and the classification report. And you can see it's a little bit different, is that in this case, for confusion matrix, there are three samples that's not correctly reported. Okay, so this is the example about the logistic regression for classification. And next, let's take a look what the confusion matrix and what are those concepts? Okay, let me find, yeah. Okay, so let's see. What is confusion matrix? Okay, so confusion matrix, so in our case, it's binary class. We have 0 and 1, okay, or 1 and 0, okay, either way. But anyway, so this is the actual, and also over here, that's the predicted 0, 1, or 1, 0. So that's predicted, the head one. Okay. So the diagonal are always the correctly. So this means true positive. And this means true negative. So that means correctly predicted. So over here, so this means false negative. And this one is false positive. Okay. And if you have more than two class, then like you have actual 3, actual 4, as here, then you have 3. Then so it depends on how many classes. Then the matrix is like n by n. Okay, so that depends. So this is regarding confusion matrix. So it will directly tell you the number for the correctly predicted and wrongly predicted, and also positive or negative. Okay, like those information. And there are some other metrics, if you recall, for the classification report in scikit-learn, sklearn. Okay. And accuracy, we already know. So that's the diagonal versus or add together. Okay. And there are some other performance metrics like recall. What is recall? Recall is only considered true positive versus the true positive plus false negative. So basically, if you recall, it's the true positive over the addition of the numbers in this row. Okay. So then what it means is so that means if the value is high, then that means the false negative is lower and the true positive is higher. Okay, so it reflects these facts. So it doesn't just give you the overall accuracy, it also review more information. And the precision is about true positive versus the addition of true positive and false positive. So false positive, basically it's this value versus the addition of this column. Okay. So then what it reveals is if the value is high, that means this false positive is also lower. Okay, so that's what it reveals. And then what is the F measure? So F measure, then it's the recall and the precision times together, then over the addition. Okay. So, and also F measures has always been nearer to the smaller value of the precision or recall. So it can give you more idea about the performance metrics. Okay. So this is about the confusion matrix and the classification reports, other performance metrics. And next, let's move to another model in this chapter. Okay. Okay, and the third model in this chapter we cover is about clustering. Okay, so clustering then it belongs to a different category of modeling. Okay, so previously what we learned like linear regression, so that's for continuous value prediction. Okay, logistic regression, this is for classification, but both of them involved with the dependent variable y. Okay. And so this kind of modeling in machine learning, we call it supervised learning. Supervised learning, that means you have the targets, okay, and you do the training, okay. And for clustering, it's different. So clustering normally no dependent variable. Or you don't count on dependent variable. Okay, so all your model is regarding independent variable. Okay, or only about the features. Okay, and you are not going to do so. No prediction involved. No prediction involved. Okay. And this kind of, so if there is no prediction involved, only discuss about independent variable, this kind of modeling in machine learning, we call it unsupervised learning. So unsupervised, okay. And clustering is one of the approach to do unsupervised learning. There are other approaches, okay. So here we just pick one. And for clustering, there are also a couple of other approaches. And here we just pick the k-means clustering. Okay, so what is k-means clustering? So the idea is you are going to group data points, and all the data points have only have the X values. Okay, so you're going to group them into K different clusters. Okay, and how do you group that? It's using similarity in the features. Okay, so similarities in the independent variables. So what is that? We will explain more. Okay, and this number you must predefined. Okay, predefined. So later on we will also see, but sometimes you don't know. You just have the data, you have no idea. Then how do you know? So then you do try. Try, and then using some metrics to pick the optimal number of clusters. So in this diagram, it also shows, okay, so here you can see we have data distribution, okay. So basically you have no idea, okay, you have two features of the data distributed here, okay. And then here, okay, we say, okay, we want to have three cluster, okay. With three cluster, you see there are three big red dots. So basically they are centroids for each of the cluster, okay? Then based on, over here it says similarity. Based on similarity, then you see you can group them into their own group and represented by their own color, okay? So this is the basic idea about clustering, and k-means clustering. It's quite useful, okay, for the k-means clustering. So how it works? It's pretty straightforward, we can see. So you randomly pick the centroid. So you have all of those sample points. All of these are are the sample points. Then you pick K central points. So you can kind of say, okay, I want to have this as a central point, and then I also pick this as a central point. I use a different, and then suppose you have 3 clusters. So K is 3, okay. And then I also define this as a centroid. So after you define of this centroid, so here I have a new sample point, is it? So which one you should assign this sample point to, is it? So you measure the distance between this new point and the 3 centroid point. And then you use the minimum one, find the least distance one. Then it's clear this one is the closest one. Because if it's the closest, then we say, okay, it's more similar. It's more similar. Okay, so then you say, okay, I'm going to assign this data point to this group. Okay, so it's a star. Okay, and then suppose you have this point. Okay, for this point, then you see the distance you can measure. Is it with then clearly it's close to the square one, so it belongs to the square cluster. Okay. And after you keep adding the point to each of the cluster, then the centroid also going to move. So suppose you have more, is it? Then the centroid also going to move. So maybe this will be the new centroid, and this will be the new centroid, and this will be the new centroid for each of the cluster. Okay, so you can keep doing this. And until what? Until your cluster assignment do not change, or the user-defined tolerance, or some maximum number of iterations reached, then you stop. Okay, so that's the idea about the k-means clustering. It's pretty straightforward. But like we just said, okay, with the K should be predetermined. But how many is the optimal, is it? So there's some approach. So the only way is we try, is it? You try with 1 cluster, 2 cluster, 3 cluster, 4 cluster, 5 cluster, 6 cluster, is it? So what is going to be the best number? So there are 2 techniques. One is called arable method. Okay, so arable method, it will use the change of the within cluster sum of the square of arrow, okay, to determine. We will see that, okay, in our example. The second one is going to use the silhouette value to measure. And the silhouette value basically is that it calculates for the silhouette coefficient for each data point, and it range between 0 to 1, okay? If it's close to 1, that means the similarity is very close. And so that means it's in the specified cluster. Okay, if it's -1, then definitely that means it's in wrong cluster. And if it's close to 0, that means it's in the boundary between 2 cluster. Okay, so close to 1 is better. Okay, so the higher score of the silhouette indicate the better separation. Okay, so you can combine both of this for the optimal choice of the K values. Okay. Okay, so this is the idea about the silhouette, the clustering. So next, let's take a look at an example. Okay. Mm. Okay, so over here, we are going to do the uh, k-means clustering. Okay, to do k-means clustering, you need to import. So this is machine learning, not the statistic model. Okay, so for the k-means, we only it belongs to machine learning, so we only introduce the machine learning model for k-means. Okay, and the data pre-processing and all of this are basically for unsupervised learning. We don't um, for the confusion matrix, normally we don't need to do that, okay? Because there is no or y prediction, is it? So that doesn't need. But over here, we just try to, we are also going to try to see like how many correctly classic, not how many samples like correctly put to the to the cluster that it is supposed to put, how many not put in the right cluster. Okay. And over here, we are going to use that traditional iris data set. And this data set itself is for supervised learning because it does have the Y value. Okay. But because it's for flower, different flower is based on the features like saddle lengths, with petal lengths, and weights. So I just use the features, the lengths and weights of saddle and petal, and try to do classification, okay, to see how it works. So let's first take a look what the data looks like, okay. So the data, you see it looks like, so the first four columns are about the X, and the last column is Y. And here, because we do clustering, so basically we don't even need this. Okay, and over here, yeah. So over here, we collect the independent variables, okay, the features for the four columns. And after you have the X values, then you see it's pretty straightforward. You just initiate the k-means, okay, model, and you need to specify the number of cluster. So because here we know there are three clusters, so we try, okay, with three cluster, and then you can predict uh, for each of the sample to see how it works, is it? And so that's why over here we try to see how close our prediction is based on the uh, clustering, k-means clustering method, okay? Because in this example, specific example, we do have the Y one, is it? So after we have the three cluster, then we can compare if some of the samples correctly grouped to it's supposed to be group. Okay. And so of those, just some very general operations for pandas and NumPy and Python operation. So we are not going to explain that, okay? We can just directly go ahead to take a look at the result. So the result, from the result, you can see is that the number of different is 17 numbers. So our key point next is for the clustering, because after we predicted is that you can also do the plotting, okay, to show in different group. So here we use a convex how, and so here it gives the cluster visual. And over here, we only pick 2 features, okay, because we have 4 features, but we only pick 2 features for demonstration, okay. Okay, the next one is a key point about the optimal number of cluster, okay. And we said we are going to use the within cluster sum of square. So basically in K-means it's called inertial, okay? So you can use this inertial to find the optimal, okay? So in this case, we change the number of clusters, so 1 to 11, okay? And for each of that, you do the K-means, and you collect the inertial, okay? The inertial basically it's the WCSS, okay, value. After that, we can plot with the inertial versus the number of cluster, okay? Then let's see what it looks like. So you see, the x-axis is the number of cluster. Okay, we have 1 cluster to 11, is it? And the y value is the inertial value. Okay, so arrow value. So arrow method, that means the optimal point is on the arrow. So this looks like an arrow, is it? So arrow, see, basically it means the arrow drops not that much if number of cluster increase. If number of the class. So you can see, yeah, you may say, okay, this looks like an arrow point, but you see the arrow still drop compare with from 3 to 4. You see the arrow still drop a lot, but from 3 to 4 and from 4 to 5, the arrow drops very little, is it? So that's why, based on the analysis of this arrow method, we think, okay, so number of cluster 3, number of cluster looks like it's optimal. Okay, so that's regarding the arrow method, the analysis result. And the other one that can make a recommendation for optimal number of cluster is silhouette. Okay, using silhouette score. Okay, so how do we do that? So here we didn't try from 1 to 11. We just try 2, 3, 4, 5. Okay, number of cluster using silhouette. And so for each of that, we do k-means. But this time, the centroid, if we don't specify, by default, it's random centroid. Okay, and here we use k-means plus plus. Plus plus means the centroid is the furthest away point. That makes sense. It is further away, the possibility to be in one cluster is lower, is it? So you pick further away, then it's maybe the different cluster. Okay, then gradually you see you can move the centroid to the center of their cluster. Okay, so that's using k-means plus plus what it means. And then after you train, then you can predict, okay? Okay, and with the cluster, is a different cluster, then here you can do the silhouette calculation, okay? And with the silhouette calculation, then you can plot the silhouette values regarding the number of clusters. And here basically it's a horizontal bar plotting, okay? And then we can take a quick look at the result. And for the two cluster, we see, so this is a silhouette, okay, two cluster. You can see, so this is the average, okay, and here is a silhouette score. And you can see it's also pretty good in this case, two cluster, okay. And if we take a look, three cluster looks like it's not as good as two cluster, is it? So yeah, so in this case, there do have two cluster that's more close compared with the third cluster. And if you take a look at the four cluster, it's even worse, is it? And with the fifth, it's not good, the silhouette. But compare the silhouette value and if we combine both, is it looks like the elbow, so with three cluster, it's optimal, is it, if we combine both, okay? So that's why over here you see, okay, we can select the optimal number of cluster as three. Okay, so this is the idea about clustering, and we can clearly see clustering has nothing to do with prediction, is it? So it's an unsupervised learning. So it's just to group the the data points into different cluster. Okay, so different clusters, they may have different patterns and their own features. Okay. Okay, so that's all of the models in this chapter. So just some brief introduction, okay? Because a modeling itself has a lot of topics. It depends. You want to go to with a statistical model or you want to go to with a machine learning model. For statistical learning, there are a lot of topics. And for machine learning, also there are a lot, and we just gave some very basic introduction here. Okay. Okay, so that's all for today.